And here we are. Hello, everybody. Welcome to CERN. We are here live today from two of the four major LHC experiments at CERN. My name is Claire Lee. I am a physicist from South Africa, working for Fermilab here at the Large Hadron Collider. Who else do we have on tour with us?
Not yet.
Okay, so over at ATLAS, I think there we have Delia and Mohammed. They're waving to us there. Can you guys introduce yourselves?
Okay, hello everybody. My name is Mohammed Al Faroub, and I am a Palestinian physicist working at Warwick University in UK. I am an ATLAS member physicist since August 2006. I have worked on topic work on W boson, and I contribute to the detector operation.
Okay, hi, my name is Delia. I am a Colombian physicist. I am currently working as a postdoc in Triumph Laboratory, which is located in Canada, but I'm based here at CERN. I usually work in dark matter searches, also a little bit of Higgs, and in the performance of the reconstruction of jets and the missing transverse momentum that we can talk about a bit later. And yeah, that's it. We are super happy to be here, and welcome to this virtual visit.
Thank you so much. Under my feet, Andres, can you introduce yourself?
Sure. Hi. So my name is Andres. I'm a particle physicist from Puerto Rico. I grew up in Puerto Rico, and I got a PhD in the States, and I've been doing research with CMS for quite a few years. And I work specifically on luminosity measurement, which roughly speaking is basically counting the number or the rate of interactions in our detector. Thanks.
Right. Thanks. And for those of you who this is the first visit to CERN, right now, what is happening is the LHC is actually not running right now. It's what we call a technical stop, where those of us who work on the detectors can use this time to do some commissioning. The people who work on the accelerators can also do some work on the accelerator side. But this allows us a really, really special time because we are able to take you into the experimental caverns to see the detectors. So Andres, where are you walking through right now? What's going on there?
Hi, Claire. Yeah, so we are making our way to the detector, but we are currently in what we call the counting room or the service cavern. And you can have a quick look here. We have a ton of electronics that are, their services. These, for example, are for reading out parts of the detector. And we have many, many complicated parts inside of the detector. A lot of the signals come in as fiber optics, and we have these electronics that read out the information. These in particular are related to the muon systems. We'll talk about these a bit later. And specifically, they're also part of the trigger system. And I'm also sure we'll talk about that a little bit. But we'll make our way to the detector itself in just a minute.
Okay, excellent. While you're doing that, Mohammed and Delia, can you maybe tell us what is a muon and what are those big things that you're standing next to?
Yes, so actually here we are in the Sumatra detector cavern. So here you can see the muon wheels, but actually this detector is huge. It's approximately 25 meters tall and 47 meters in long. So it's a very cylindrical structure. It has a very onion shell-like structure with different types of subdetectors going from inside to outside. So basically, in the outermost part of the detector, we have the different muon detectors, which are called muon chambers, or these muon wheels, which are very nice. You can see here they are huge. So this is what we are seeing now.
That thing is absolutely gigantic. Mohammed, how large is the ATLAS detector?
So ATLAS detector is like a digital camera. It's the largest among the LHC experiments. It's 50 meters long by 25 meters in diameter. And it weighs around 7,000 tons. It is the largest in size, but it's not the heaviest. CMS, your experiment's much heavier than ATLAS. Your experiment around 14,000 tons. Our experiment is half of that, 7,000 tons. But we have the largest size.
Yeah. Just to give you a little bit of perspective, this is the it weighs more or less the weight of the Eiffel Tower. So, okay, it's not that light.
Oh, but that's still really, really, really large. It's you know,
Okay.
an Eiffel Tower's worth of electronic components. And you guys are on the bottom floor, I see, looking up at the detector.
Should we start at the bottom?
Yeah, but I actually just want to ask Mohammed and Delia, where do the particles actually collide inside ATLAS?
Yeah, so basically here you can see the beam pipe, more or less, this blue thing. So basically the protons are coming in this direction, and symmetrically in the opposite side is exactly the same thing. The protons come in the other direction. So then they're 33 meters away from here. They collide in the heart of ATLAS. So we managed to collide them, and then they produce a tons of particles. And then our different subdetectors are there to try to catch the different signals.
That's amazing. By the way, for those of you watching, if you have any questions, feel free to just type their questions into whichever the chat, and we will do our best to answer them for you. Andres, what does the CMS detector look like?
Hey, Claire, thanks. So this is CMS standing just over here behind me. And as Mohammed and Delia were saying, CMS is much smaller compared to ATLAS, but it's still very, very big. So we're talking about 15 meters tall. You can see just when I stand next to it, I'm very, very small compared to the detector. And yeah, it's a very heavy detector, so almost twice as heavy as the Eiffel Tower. It's like 14,000 small cars. That's the weight of the CMS detector. And you can see sort of the outside of the detector. It's, you know, there's many, many layers inside of layers, a lot like a cylindrical onion. And CMS in particular basically takes that concept, but we slice the cylindrical onion into about a dozen slices, and we can actually move them apart. So you can see the system that we have in order to move these slices. So we have to rearrange things quite a bit, but then we actually take these orange feet. We can blow compressed air through these things, and they act a bit like a hovercraft. So it can lift these slices just slightly, just enough so we can move them without friction. And that's the way we can move the slices in CMS.
That's amazing. And so you said it was about 2 times the Eiffel Tower. That's what, 14,000 tons?
14,000 tons. And in fact,
sorry, yeah?
Yeah, so in fact, there's a lot of steel in our detector, which is related to the magnetic system. So we have a very large magnet inside of our detector. It's a 6-meter inner diameter magnet by 12 meters long or so. And outside of the magnet, we have 12,000 tons of steel in order to channel the magnetic field outside of the magnet. And that gets us about 2 Tesla outside the magnet and about 3.8 Tesla inside the magnet.
Wow. Is the magnetic field on right now?
No. So the magnetic field is not on at the moment. So this is part of the maintenance that's taking place. If the magnetic field was on, it would be very noticeable. So anything, even the camera would be affected because of the autofocus in the camera. I've heard of people that take safety shoes, and these are steel-toed. If they are magnetic, then you will walk very funny in here because your shoes are being attracted to the magnet.
That's amazing. Let's go back over to ATLAS. So we have some really good questions coming in right now. So first things first, Andrea would like to know, why do we need to have such large detectors? Mohammed, can you answer that for us? Why do we need such big detectors?
We collide extremely fast protons. I mean, protons at the LHC travel with 99.99999% of the speed of light, and the outcoming particles are also extremely large. So we need large, extremely fast, sorry. So we need large detectors in order to measure their tracks with high precision. And of course, measuring the tracks allows us to measure their momenta and the charges. Also, we need large material or calorimeters to stop those fast particles to measure their energies. So if we collide fast protons, the outcoming particles will be very fast, and to measure their charges, momenta, energies, we need large detectors.
Yeah.
Right. Wow. And
something I want to add on this,
sure.
Is that you know that charged particle bends with the feeling of the magnetic field. So we also have magnets here that are super powerful, and they are super nice because they are toroidal. So they have this very toroidal shape that goes through all the detectors. They are huge, and they create this magnetic field to make the charged particles bend. So if you have, for example, an electron is a charged particle, so it will bend. And by the bending of the particle, we can know if it's positive or it's negative, or if it's not bending a lot, if it's super fast. So for example, it has a lot momentum, or if it bends a lot, it is a very slow moving electron. So for example, we use these magnetic fields, and it has to be this big, so we can really measure very well, as Mohammed says, the momentum of the particle, which is a very important quantity for us to measure.
Thank you so much. What can we learn about the universe by studying such tiny particles? Delia, do you want to tell us a bit about what you're working on, for example?
Well, here, the interesting point is that here we are looking for the building blocks of the universe, the tiny little pieces that form our universe and how they interact. So these fundamental particles are all the particles that are inside the Standard Model, which is our theoretic model to describe the universe. But it's super interesting because the particles that we know is just 5% of the total content of the universe, only 5%. So this huge detector, this huge accelerator is just studying 5% of the content of the universe. And there is a very important big question currently in particle physics, and is what is the dark matter? Dark matter, it's something that is there in the space, making the galaxy rotate, so we know it has gravity, so it could be a particle. Everything that has mass, has gravity, is a particle. So we are trying here to go beyond this 5%, to try to collide protons, and since it goes up very fast, it goes up to the velocity of the light, well, a little bit below, but almost to the velocity of the light. So we can create particles as if they were created at the beginning of the time, at the Big Bang. So we are kind of trying to reproduce the conditions of the Big Bang. So if there is a dark matter particle, we are maybe able to produce it, and so maybe we are able to detect it. So this is something very interesting we can understand from the universe, and a very important question currently.
That's really, really cool. Thank you so much for that answer. Mayul has a very interesting question about CMS. So Andres, perhaps you can tell us why do we need to be able to move these layers of CMS? Oh, look, you're up now.
Yep. Yeah. So in CMS, we often have periods of maintenance, and as Claire was saying at the beginning, we're now in the technical shutdown. So this is the second technical shutdown we've had this year. And it's a period where we go in and from the LHC, from CMS, from ATLAS, and from all sorts of experiments in the LHC, people go in and do maintenance work, for example. And for CMS, in order to access certain parts of the detector, we need to open up the slices. So you can get a good view from here. We're standing almost at the top of CMS, and you can see this red disk is part of the muon end cap. And you can see this orange section over here. So that's actually shielding. This is the new shielding actually that's in place for an upcoming upgrade in a couple of years. So it's already in place here. And you can kind of get a good idea of the dimensions and the shape of CMS here. Another thing I wanted to show is if we can look up, we can see that CMS had to be lowered down. So each of these slices was lowered down one at a time through this this elevator shaft, or not elevator, the main shaft, I mean. And there's a couple other things you can see in the sort of ceiling of CMS, but maybe I pass it back to you.
Okay, yeah, thanks. Mohammed, these experiments are huge. How many people does it take to run something like this and work on this? And what are the types of things that people do when working on this experiment?
So in ATLAS, we are around 5,500 collaborators. Large number of the ATLAS collaborators are engineers working in cooling and ventilation, or electronics, or pure detector development. Some of them in data acquisition or trigger, because we need to filter the events, not everything, or the collisions, not every collision is recorded, and around the 3,000 physicists. So we have wide range of expertise physicists, computer scientists, we have mechanical engineers, electronic engineers, we have students, master students, PhD students, we have professors. You can find every type of science in ATLAS.
Absolutely. That's really, really awesome. What if we found, since discovering the Higgs boson, this is a question from Nefeli. Maybe Delia, maybe you can answer that. What have
Sorry,
we
can you
learned?
repeat?
What have we learned since the Higgs boson was discovered?
Well, we discovered the Higgs boson in 2012, and it was a major discovery because the Higgs boson is in charge of giving the masses to the fundamental particles. So that's a big breakthrough. After that, okay, so we have a particle that is likely to be the standard model Higgs boson, so the one that we think in theory gives the masses to the fundamental particles, but the story is not over. We need to really understand if this particle is really the standard model one, it has the properties that we expect, it is the scalar with the mass, with the different properties, or maybe there could be another types of Higgs bosons. Similar particles that can be also in charge to giving masses to the other particles and interact very similar. So we are trying to understand very well the Higgs boson, its properties, and if maybe the sector of the scalar boson, or what we call the scalar sector, its extended, is huge, it has more particles. So this is something we are trying to figure out after the Higgs boson discovery, or there are other theories that are beyond the standard model. For example, supersymmetry is another property we are trying to study. The quantum, if there is a quantum theory of gravity, so trying to find gravitons. There are too many theories that we are trying to prove and test with our nice detectors.
So here's a fun question from MG. Since you work on dark matter analyses, Delia, what is the model that you're hoping is the one that actually describes what the universe is doing?
There is something nice for the dark matter is that we have tried so many different models, and we try to think maybe that the models are simple, but currently, and this is very mainstream right now in the world of theoretical physics for dark matter, we think that maybe there is a dark sector. It's not just one particle that is in charge of being dark matter, but instead there is a huge amount of other dark particles, like super similar to what we have in the standard model. And maybe in this dark sector, they are having dark interaction, there are new exotic particles that interact very feeble, very weakly with the standard model. But there could be different kind of dark matter particles. It can be a composed dark matter. It can be formed, for example, of an hadron. Here we are colliding hadrons. The proton is a hadron. But maybe the dark matter, our cell phone light, the dark matter is an hadron, it's a composite particle. So this could be a very nice theory, and the one that I'm working on right now, that the dark matter is coming from a dark sector, and maybe it's a composite particle, not just a fundamental particle. This is what I would hope that dark matter could be. That will be the most interesting scenario.
That sounds excellent. Good luck with that. Andres, what about black holes? Could the LHC create black holes? That's a question from Moon.
Okay, so that's a really interesting question. So the answer is we don't know. So under certain models, it might be possible, but the leading, the converged. How do I say this? Most experts think that if a black hole was created at in the LHC, it would evaporate immediately. So there's a phenomenon called black hole evaporation. So whereas a black hole essentially emits particles, which is complicated because you have probably heard that black holes, nothing escapes a black hole, but at the event horizon, things are complicated. So in any case, there's this thing called evaporation. This is something that Stephen Hawking proposed. So if a black hole was produced, we will be perfectly safe. And in fact, we are receiving particles all the time from the cosmos that hit the Earth of much higher energies than the LHC can produce. And we're still standing here, no problem. So we know we're safe. if we were to produce a black hole, that would be really exciting. There's a lot of people that are developing studies to try to see if we can produce these type of particles. It would be very, very interesting if we could, and we could try to study that if it could happen.
So I guess the thing is, yes, we would like to get them. It's not dangerous if we do, and it would be very, very exciting if we found them. What about some of the other hypothesized particles like gravitons or even tachyons? Those are questions from Julian and Somesh.
Yeah, so all of these particles are, things we're trying to find. And maybe not to, I mean, I would say the same. There's people that are studying and doing analyses to try to see if we can find these particles. There's a couple of things that I would mention, right? So it's clear that these would be extremely rare events. So this is why we want to constantly collect data. We want to take as much data as we can. And in a few years, we're going to upgrade the LHC and all of our experiments in order to collide particles at a higher rate so that we can collect more data more quickly. And that's the point, right? Is we have some processes that occur very, very rarely, and we want to study exactly those. And then there are some processes that we have never seen before, and maybe they occur extremely rarely. So we've never seen them. We really have to collide, have collisions at a high rate, collect a lot of data in order to even find them. And one last thing about this whole business, right, of like colliding particles. What you really want to do, right, is we have a prediction from the standard model so that you can solve the standard model, which is a set of equations that we've developed over hundreds of years, right? It takes, special relativity, it takes quantum mechanics, it takes a lot of, theories and a lot of established physics, puts it all together, and we can actually predict what happens when these particles come together. We do that over and over, so we can simulate this in a computer. We have a simulation of our detector. We predict how each particle is going to interact with each part of the detector. And once we have a lot of these predictions, right, of a lot of these simulations, simulated events or simulated collisions, then we can compare it with the data, and we see how well they match. And if they don't match, right, so that there might be something about your prediction that is inaccurate, or there might be something about your observation, your measurement that's inaccurate, or maybe there's something new that you have never seen before, so you have not accounted for it in your prediction. So we do have all these particles like tachyons, and we have a number of hypothetical particles, but even more exciting would be to find something that nobody has dreamed up, some new phenomena that nobody has thought of before. That would even be most exciting. Okay, so we're gonna walk around a little bit more so you can see more of our detector as well.
All right, yeah, we'll keep it going while you guys are taking us on a little tour. I just want to tell everybody watching, yes, this video will be available offline on the YouTube channels, so you can catch it there. Thank you so much for your comments and questions. Just by the way, Andres Dida Mohammed, we've got some great comments saying that it's fantastic to see the guts of the ATLAS and CMS experiments.
Maybe I can quickly add, so what we're doing right now is something you would never be able to do if you come visit CMS. So this is also a great opportunity for us to show you places you would never be able to access in person. We're standing literally on top of CMS. The detector is under my feet, and this is the CMS detector from a view that you would never get, even if you come here to CERN. Come check it out.
Yeah, and you can even see the slices sort of in this shot.
Yeah.
What about over at ATLAS? I think you guys also are in an area that you don't normally take visitors to, right?
Actually, this platform we can bring visitors to this platform occasionally. It's the second floor, but beyond that sign we cannot take visitors.
Okay, cool. But everywhere else that you've been today, so it's places.
No, here, for example,
visitors
cannot come to this area. So I'm walking towards side C. So side A, next to the airport, side C, and this is the barrel. So A, B, C. So let's go to the other side of ATLAS detector.
Thanks, Mohammed. And there's a lot of questions, particularly one from Mayul, who would like to know how can he come and work at CERN?
Oh, there are many ways to work at CERN. I mean, if you are a bachelor student studying physics or engineering, and in your second, third year, you can apply for CERN summer school.
Okay, cool. How did you come to CERN, Mohammed? I think we lost them. Oh, here's a really, really nice question about when we have these collisions happening. Do we have secondary or other collisions too? Andres, I think you're probably, because of your work with the beam, this is a good question for you.
Yeah, sure. So that's also it's a very interesting question. I don't know what people have in mind when they think of collisions at the LHC, but what we actually have are groups of protons that are circulating around the LHC. So it's not individual. We don't even think of them as individual protons, right? We have bunches of protons. That is exactly what we call them. And in each of these bunches of protons, we have about 100 billion protons, which sounds like a lot, but these are very, very tiny particles. So when we have the collisions, we have about 100 billion protons, and we actually squeeze these bunches of protons to about the width, actually smaller than the width of a human hair. And then we cross these bunches, right? So we make them get as close to each other as we can under current conditions. So if you think about that, right? So, you might think that a ton of them would interact, right? And while you have to think of the scale though, because these are extremely tiny particles. So in fact, when we cross these hundreds of billions of protons in the current LHC conditions, we get maybe 50 or 60 of them that actually interact. And that happens at up to 40 million times per second, which is every 25 nanoseconds. So that is the current sort of rate of interactions we expect from the LHC. And that means, as the question sort of suggested, that we have indeed many simultaneous interactions or collisions. So we have to select events that are the most interesting. So that means that at least one of these interactions was a very, very, let's say, a very interesting interaction, right? And the way you can tell can be simple because you have protons and gluons you have quarks and gluons inside the protons. When they interact, you might expect, well, more quarks and gluons, right? Which is true most of the time. But when a muon comes out, you're like, where did the muon come from? So that means that there's a lot of energy exchange, and from that energy, we were able to create mass, right? E equals mc squared. We took the energy, and we got a muon out of that. So that is something we can use to trigger that event, right? That means we select that event and we record that event. And so we have some trigger experts here with us from ATLAS, so I can let them elaborate if they wish.
Right, yeah, I was actually just going to ask, because you said 40 million times per second.
Yeah.
Delia, how do we handle all of this information? And Jordy wants to know if we have the computing capacity to handle all of this right now.
Yes, can you hear us now?
Yeah, we can. Great.
Okay, awesome. Yeah, so basically this is what we call the trigger system. So, well, okay, we have collisions every 25 nanoseconds. So there's a huge amount of collisions. We cannot save all of them. We cannot study all of them. So there is a hardware trigger. So the detector has ways to select which collision is interesting, which no. So interesting, not interesting. And then we have a computer-based trigger that kind of super quickly reconstructs some important parts of the events, for example, a muon, and select, okay, this is an interesting event. And all of these, okay, is called the trigger system, which allow us to kind of diminish, like make the rate of how we say what we save in data much, much less. So we are able to analyze interesting collisions. So this is very briefly how it works.
Mohammed, do you want to add anything about the triggers or maybe the computing side of things?
Yes, so as Delia said, we have 14 hours, Andre, it's the same rate of collisions, 40 million collisions at each experiment. And most of the collisions are pure elastic collisions or pure electromagnetic repulsive force, which means two protons colliding, and out of the collisions, two protons. Those don't provide any new knowledge, and those what we can filter out. So we have two levels in ATLAS. Level 1 is decided by the detector itself, and we can reduce the rate from 40 million collisions per second to 100,000 collisions. And those collisions will be transferred to a computer farm upstairs, around 40,000 computer nodes. And there we run the software, fully construct the collisions, and then we look for unique signatures. For example, we can look for electrons with a certain momentum or minimum momentum, or muons, or photons, or jets. Jets are a group of particles originated from quarks, or other signatures. And if we find any of these signatures, we keep the collision. If none, we can delete the collision. And by doing that, we can reduce the rate these days from 100,000 collisions to 4,000 collisions. And it sounds a small number of collisions kept, but if each collision occupies on the hard disk 1 to 2 megabytes of bytes, which means we need 3 gigabytes, or we store on the hard disk 3 gigabytes per second. At the end of the year, we end with 20 petabytes. It's a huge amount of data.
That's amazing. There's some great questions here. So since we're talking about the collisions themselves, Bookmarks has just asked us how many particles are generated in one collision, and I guess it just depends on what they're looking for. Maybe each of you can tell roughly in the type of things that you're looking for how many particles, if it's lots or few or what. Delia, do you want to start?
Okay, yeah. Well, it's important first to understand a bit that what we are doing here with all these huge detectors is not that it at the same time reconstruct all the particles. It has different sub-detectors. So for example, very in the center of the detector is the inner detector, which is basically a megapixel camera. It has a lot of pixels. So it records where the particle passed by. So it tracks. So basically there we record charged particles, for example, an electron, a muon. Then we have the calorimeter, where the particles is basically they destroy it. So the particle comes and then it gets destroyed by the calorimeter, and the calorimeter saves how much energy the particle leaves. And then this is for hadrons or more like heavy or particles. For example, that's how we reconstruct the jets. These showers of particles, all of them are stopped in the calorimeter. So we reconstruct different calorimeter cells saving energy. And then in the outer part, we have the muons. So all of these sub-detectors have different ways of recording different types of particles. So for example, in my analysis, I love the jets. Jets are awesome. They are huge. They have a lot of interesting things. They have inner detector. They have calorimeter. So there is this bunch of shower of particles, and it's very nice to see. This is what we call hadronic activity. So we have hadrons, but we have even two types of calorimeters. The electromagnetic to record photons, and well, basically, yes, particles that are coming from the electromagnetic part, and then there is the hadronic part for more heavy particles like composed particles. So the jets are these huge particles, and these are very useful, for example, for dark matter searches. We can have dark matter. Well, dark matter doesn't not leave any signature. So what we do is to try to reconstruct very well a huge jet that is not recording against anything, that is nothing in the other side. So we are like thinking, okay, something here is missing because the missing transverse momentum, the conservation of the momentum it's not zero, it's not conserved. So something has to be missing that we don't observe, and this can be dark matter. So jets are a super nice tool for searches, for example, dark matter searches. And I love them.
You are underground.
My favorite reconstructed particle, Mohammed.
What's your favorite particle, Mohammed?
I don't have intimacy with particles, but I work on top, so I like topic quark, and actually it's a special quark. It's the only quark that decays before it's converted into composite particles, and so it allows us to study the bare quark, the weak interaction. Other quarks is much harder to do to study them before they hadronize or again converted into composite particles. Another particle that I love is the W boson. It's the force carrier of the weak interaction, and it decays very fast. We study it. We study the weak interaction. We can test the standard model of particle physics, and if we see deviations, we might learn new things and or hints for a new physics.
What about extraterrestrial particles? Andres, you are underground right now. Have you ever detected particles coming from outer space?
Yeah, hi. So I guess the question is, can we see particles coming from outer space? And it turns out that we are 100 meters underground right now. The floor of this detector is 97 meters. In spite of that, we actually do see muons in our detector that come from outer space. So we actually, as I mentioned before, we get a lot of particles coming from the cosmos. These are called cosmic rays. And in the atmosphere, some of them interact and will produce a highly energetic muon. There's other stuff going on, but that's just an example. And muons, which, by the way, since you're asking about favorite particles, I think muon is what I would say, and not just because it's part of the CMS acronym, so compact muon solenoid, but I think that it's also pretty cool.
I like muons.
And so muons actually are a lot heavier than electrons, but otherwise pretty similar. And what that means is that when they carry enough speed, right? So if it has a lot of momentum, it's really hard to slow them down. So these are produced in the atmosphere, and a lot of them just go straight through the Earth. And we can see some of them go through our detector. In fact, that's typically what we're doing, where when we don't have collisions, we can run our detector and measure these cosmic muons in our detector.
What about neutrinos? Can we catch those in the detector?
So neutrinos are more difficult. Neutrinos are particles that are electrically neutral, and they have a very, very small mass, and they only interact via what we call the weak force, the weak interaction. So that means that for a neutrino to reveal itself, it has to interact, it has to talk to the nucleus of an atom. And so a neutrino typically just punches straight through the Earth. The sun is producing trillions of neutrino. In fact, right now, wherever you are on Earth, there are trillions of neutrino going through your fingernail every second. And they really don't do anything. They just, they don't talk to any of the other particles usually. So in our detectors, we don't directly see neutrinos. There are other experiments around the globe that are dedicated to measuring neutrinos, and they usually have some big tank of some kind of fluid, and then they can detect the interaction of the neutrinos. But in the context of the LHC, so in CMS, for example, we have to be a bit more clever if we want to deduce that there was a neutrino. So what we use is conservation of energy. So when we have collisions, before the collision, all the momentum is traveling in the direction of the particles. So if you sum the energy in this plane, in the transverse plane, before the collision, there's basically no energy, right? So it's zero if you look at the energy in this plane. And so after the collision, we look at all of the particles that emerge and we count the momentum or the energy that they carry in this transverse plane. And if it doesn't add up to zero, it can indicate that there was a neutrino in that interaction. It's an indirect measurement, but this is what we call missing energy, and this is one of the techniques that we use to deduce the production of a neutrino in an event.
Amazing, thank you. Here's a really interesting question. Why have we decided to collide protons in the LHC and not, for example, electrons? Delia, would you like to give?
Yes.
Oh,
no, go ahead.
Would you like to give that a bash? Why are we colliding protons? Why aren't we colliding electrons, for example?
It was initially, it was thought to collide protons. So I think for the setup for colliding electrons will be very different from this. Well, we not only collide protons, we can also collide heavy ions. Mm-hmm. But initially this is optimized and it was thought and built for colliding protons. But maybe that Andres is more into LHC will know why we can collide electrons.
Sure, yeah, I can provide a little bit more information. So in fact, if you're old enough and you were into science, you know, I don't know, 30 years ago or so, you would have heard about the Large Electron Positron Collider. So back in the 90s and 2000s, we actually used the LHC tunnel, this 27-kilometer tunnel that goes, it's 100 meters underground. It goes around the Swiss and French countryside. In the 90s and 2000s, it was initially used to collide protons and electrons and anti-electrons. But the reason we don't do that nowadays is there's a couple of reasons. One is that when an electron and any charged particle, when you change their direction, if you bend them, for example, they will lose energy. When you accelerate an electron, it would emit radiation, so it loses energy. So it's not very efficient to collide electrons in the LHC because this will limit the amount of energy that you can inject into the electrons. So we use protons. There's something called synchrotron radiation, and it goes to 1 over the inverse, 1 over the mass to the 4th power. So there's much less of this stuff going on when you use protons. It's much nicer. But there's another reason, right? So electrons are point-like particles. So when you have an interaction between electrons, these are very precise in energy, right? You in a sense, whatever energy the electrons carry, that will be the energy of the collision. Whereas if you use protons or heavy ion, as Delia said, these interactions are much more complicated. You can think of protons as, you know, containers. They're like bags that are full of quarks and gluons. So when protons interact, we often think of, or we often model it, right? Describe it as one of the quarks inside the proton talking or interacting with another quark, or maybe 2 of these quarks stuck to each other. The point is that depending on the type of interaction, the energy exchange will be different. So that means that you have a range, you can sample a range of energies when you're doing collisions with protons. For people who are into this is often said to make the LHC or Hadron Colliders in general a discovery machine versus electron colliders, which is precision measurement, if you will. But that's anyway, that's kind of what I would answer to that question.
Thank you. That's really, really interesting. So maybe Mohammed and Delia, we have a question from Federica who would like to know, you know, this type of research that we're doing here is super exciting, but are there any practical applications for what we've been doing at CERN?
Oh, that's a difficult question. So if you speak about the particle physics, like the fundamental interactions, the basic physics research, the application is far away in the future, because we need to understand the physics, the basic physics before we think about application. However, in order to make the particle physics research, we need to build detectors, we need to build accelerators, we need to build electronics, we need to train students. And that's the byproduct of our research. That's what we can use these days. But if you speak about Higgs boson and the quarks, maybe in 100 years we can apply them.
But
maybe
just
I
to
could
add on this, something very interesting is that, for example, we were talking about the trigger and the huge amount of information that is saved here. And in order to do this, in CERN, the www protocol was invented. So we can really manage to send all this information around the world. So this is quite important byproduct of the investigation. Also, there is applications in medical
but
science.
That's of the byproduct of our research, not the research we are doing.
Yeah, exactly. I mean, those are the important things.
Maybe I can quickly add something. So that's very much true that when you talk about the applications of, let's say, practical applications of the work we do, I would say that's not why we do it. We do what we do because of curiosity, exploration. We want to be able to describe the universe at the smallest scales in its most fundamental way. But as we were just saying, there's a lot of technology that we develop along the way. So Delia mentioned, for example, medical physics. So we work with a lot of superconductors, and we are constantly trying to improve them. And there's materials science that goes into this, for example. So I mentioned there's an upcoming upgrade in the future. We're gonna collide. I mentioned earlier we collide every time the protons cross. There's like 50 or 60 interactions. In a couple of years, right? In 5 years, 10 years or so, we should have 150 or even 300 interactions per crossing. In order to do that, we actually have to develop new types of superconducting magnets that use a different type of material that can produce higher magnetic fields. So it's very much possible that when we have advances in superconducting technology, for example, that makes your PET scan less expensive. When you any kind of medical imaging is using the same kind of technology. And there's a large number of other technologies. Delia also mentioned the World Wide Web protocol. Now,
which allows us to see you guys right now.
Yay.
exactly. But certainly in the future, many, many years in the future, it's certainly possible that we could leverage the physics that we study here in some way, right? So it's not inconceivable that in many years from now, somebody could use the Higgs field for something. But for us, that's not why we do it, right? It's really just exploration.
Yeah, this is basically very interesting because it's the science because of the pure knowledge. This is fundamental science. And for example, when Maxwell was writing the equations of electromagnetism, he was not interested in telecommunications. Or when Einstein was proposing the general relativity, he was not thinking in the GPS. But then these things happen later. Who knows if we will have telecommunications with neutrinos in 100 years from now? Who knows?
Right, exactly. And I think another interesting fact, during COVID, the ATLAS DAC farm, they converted it over to be used as part of this global folding at home, the program, which allowed simulations of the COVID spike protein to be run on the ATLAS computing farm, and this, contributed to the modeling of the COVID virus. So, we try and do stuff here at CERN all the time to pay things back. So there've been a lot of questions so far today about what is coming after the Large Hadron Collider. The LHC is this 27-kilometer circumference ring. Are we going to build a bigger one? What's going to happen there? Is there something more powerful that we've got planned in the future? There've been a few people asking questions about this, so I thought I would save it to the end.
So maybe I can jump in just very quickly. I'll also leave some room for our colleagues. But I'll first mention that we do plan to run the LHC. There's upgrades that we are planning, but the LHC as it is, we plan to run until at least 2040. So the LHC program is still quite a few years away from ending, right? So there's still a lot of physics to do here at the LHC. Maybe I can hand it over. And again, we're going to have this very, very significant upgrade just coming up on the horizon. So just keep an eye out for that. And maybe I can hand it over to Delia and Mohammed to talk about the maybe far future of the field of particle physics.
So there is a proposal by CERN to build a much bigger accelerator, around 100 kilometers in circumference, called FCC, Future Circular Collider. Now, if they build it, they will start in 2040 and finish in 2050. And we hope to achieve, I think, 100 tera-electron volts, like 10 times more higher energy than the energy available at the LHC. But I mean, on my time scale, it's far away in the future. Hopefully, they build something smaller so I can work on it, like maybe a muon collider, maybe 50 kilometers.
Yeah, that would be fun. But Delia, what could a bigger collider mean for dark matter exploration, for example?
Well, the bigger collider with much higher energy, because, okay, there is something important, because we have a center of mass energy, and the amount of energy is very important because it's related to the heaviest the particle we produce. So if we have much higher energy, that means that we can access much higher massive particles. And this is very important because a lot of the physics the exotic physics, physics beyond the standard model, hypothesize super heavy particles. For example, in supersymmetry, there are super heavy particles. In a lot of dark matter models, there are very heavy particles. And these particles are often used to be the portal, the one that connects the standard model, the visible sector with the dark sector. So if we have higher energy, this means higher massive particles, we can produce and probe higher ranges of the models. So this is very interesting for searches. But also we are going to have higher luminosity. And this will also be very interesting for measurements because the higher luminosity, the higher amount of collisions we have, so we can precisely, with all these statistics, measure a lot of properties that are very interesting. So for example, there is a phase of the future circular collider that is a Higgs factory. So we are going to be able to study physics to a super high precision to really understand if the Higgs is what we think is the Higgs. So that's a very interesting perspective.
And don't forget the improvement, the progress in technology, detector technology,
true.
computing, etc.
Right. Maybe on that, I don't know if any of you work on scintillators, but we have a question from Pavitra about, what is the future of the scintillator technology that is anybody working on scintillator technology there? I know some, like for example, in the calorimeter in the CMS eCal, they use scintillating crystals, right?
Yeah, so there I would say two things. So the CMS calorimeter that is in here is very, very interesting. So that's not really the question. The question is about the future technology for calorimeters. But still, I wanted to mention also to give you a sense of what kind of project the LHC and CMS is as a whole. So CMS uses these crystal calorimeters, and these are artificial crystals that are like almost 90% lead by weight. So they're extremely dense, extremely heavy, but they are made from a material that makes them transparent, and it's a scintillator. So it produces light when a particle hits it. And we use the amount of light to deduce the energy of the particle that's coming in. So each of these things has to be grown in the lab, and it takes about 2 days for each of them to be grown in the lab. In our detector, we have more than 75,000 of them. So that means that in order to just grow the crystals, it took 10 years for us to be able to have the crystals, and then we have to cut them, polish them, characterize them, glue them, et cetera, et cetera. So for CMS, this crystal calorimeter should last the lifetime of CMS. But there's other uses for scintillators, and I'll just mention one really quickly. So in this next generation or next phase of the LHC, which we call the high luminosity LHC, CMS will install a timing detector, and in the barrel of CMS, the sort of inside of the magnet, we will have a timing layer that is using a very fast scintillator and give us information on the order of a handful of picosecond, well, maybe 2 handfuls of picoseconds. So we're talking about picosecond resolution. That's where a lot of the sort of new technology in scintillator is going, is we're really fast scintillators. But I'll hand it over in case there's any other comments from my colleagues.
Okay, well, we actually have another question actually about who pays for the research at CERN. And this is an interesting question because the answer is different for CERN and for ATLAS and for CMS. So Mohammed and Didia, would you like to tell us about how the ATLAS collaboration works and maybe which countries are involved in ATLAS?
So in ATLAS, ATLAS budget is paid by the research institutes, not by the states. So CERN is different from ATLAS. CERN budget paid by 23 member states, while ATLAS is paid by 182 institutions. And so the institutions pay the running cost of ATLAS experiment, and also they build the material. And now the salaries, like the researchers like me and Delia, we are paid directly by our home institutes. And so maybe it depends whether you are working at CERN or working on the experiment, you have different source of budget.
So maybe I can just quickly mention something that I find interesting. So you might think that CERN has a huge budget. So CERN employs quite a lot of people, but again, I'm not employed by CERN, and most people who work on the experiment, CMS and ATLAS and so on, They're not employed by CERN directly. Turns out the CERN budget is like, it's something like a tenth of the budget of NASA, which is already very small when you look at the grand scheme of things. So we say that the cost of running CERN for a European in these 23 member states is about the cost of a cup of coffee per person per year. So really not a lot of money to run the most world-class, the biggest and most powerful accelerator in the world.
Oh, sorry. I forgot to unmute. How many people are working on CMS, and which countries are involved? Do we have people from all the different continents?
Yes, actually, I can show you something perhaps. So in CMS, it's roughly similar to ATLAS. The collaboration is between 5,000 and 6,000 people. And again, a lot of engineers, a lot of physicists, students, faculty from around the world. And so the actual number of countries in CMS, I don't remember exactly, but it's more than 50. I think it's 60 something, but I don't remember exactly. But I can also point out something interesting. So if you look around CMS and while you're down here, you might see some electronics that have, you know, a logo, or sometimes there's a sticker for the university team or the mascot, and you know, Go Gators, for example, in Florida. But something that's interesting here is if you look at this like red disc, this end cap, it might be hard to make it out. Unfortunately, we cannot really zoom in, but you can see that this is the flag of Pakistan.
Oh, cool.
And this is because Pakistan was heavily involved and is still heavily involved, but they worked on the design, construction, and the commissioning, and they continue to work on this detector, the RPCs in particular, the resistive plate chambers. You can see this item here. This is the support for the HF, the hadronic forward. Sorry, there's a lot of acronyms. Again, this is an item that was built in Pakistan, and it supports part of our detector quite literally. So yeah, if you look around, you can see the sort of wealth of people in the collaboration, and where people come from. They leave a mark, right? So they leave a sticker, or they put, yeah, people are very proud, of course, of their work as well.
That's great. I think Atlas has similar ones as well. And I just want to say, you know, part of what CERN does is, because it is all publicly funded, CERN makes sure that all of their results go to open access journals. So nobody has to pay to read any of the results that come out of CERN. And in addition, the experiments like ATLAS and CMS publish open data that you can go and get some data that we have taken right here at CERN, at ATLAS or CMS, and you can analyze it and you can look through it for whatever your favorite dark matter particle is. So if you're interested in doing that, just Google CERN open data and you'll get the link to find everything. So we have about like 1.5 minutes left before we have to say goodbye. And I think to close off, could each of you just tell us what is your favorite thing about working here at CERN?
Okay. My favorite thing of working here at CERN is what we were talking about. The amount of nationalities, people with different backgrounds, languages, culture, the diversity is huge. So this is my very favorite part of working in these huge collaborations, I mean, at CERN. It's very international, it's an international effort. So from different countries, from different backgrounds, everybody goes, unite for science. So this is very beautiful and very nice, and also give you a lot of perspective and a lot of fraternity and empathy for different views, and everybody has an opinion, and this is awesome. It's a very nice, interesting place.
Absolutely, thank you.
I don't have a routine. Every day I work on different things. Sometimes I write code, data analysis, or statistical analysis, meetings, some days outreach, or sometimes the detector operation shifts. Every day is different. I don't have a routine, and also physics-wise, I do what I like. Nobody dictates me, search for this particle or not, don't look for that particle. If I am interested in a search, I do it. I have access to the full data set, and I am supported by my university.
Sounds fantastic.
Yeah, so I would very much mirror exactly the same message. I would also just quickly add that I really enjoy the atmosphere at CERN in the sense that everyone you talk to is extremely qualified and they're expert in something that you may not know much about, right? So you can just go around CERN, you meet people, and they might be experts in something you never ever even thought about, and you talk to them and you learn so much interesting information. And so this applies all the time. You talk to people and they have different backgrounds, different expertise. So it's really, really cool to get to meet a lot of people. You learn a lot of stuff. And yeah, that's what I would say.
Thank you so much. And thank you, Delia, Mohammed, and Andres, for taking the time to show us around these amazing experiments underground, 100 meters underground in the France, Switzerland region. Thank you, especially to everybody who joined us today and for your fantastic questions. And we hope to see you again soon. Bye.
Ciao.
Bye.
Ciao.